Hello, everyone. Can you see my slides? Can you
Yes,
hear me okay?
yes,
Okay,
we can hear you.
cool. Thank you so much for coming. So today will be the last lecture of this module, causal models and the Wigner's friend thought experiment. So right now in the Zoom chat, I have uploaded the PDF for the slides. So the PDF is called NCC Wigner. If you would like to have the slides for this lecture, you can download there. And I also have uploaded the homework solution for the lecture that was given by Marina, and the solution, yeah, you can also download from the Zoom chat. And there's also a link. It's a link to a Google form. It's a link to get a feedback from you regarding like how you feel about the course, or if you think there's something that we can improve. So yeah, there are 2 PDF documents and 1 link in the Zoom chat. Okay, so let's start our lecture for today. As I mentioned, it's a lecture about the non-classical causal models and the Wigner's friend thought experiment. So this lecture is mostly based on a paper I co-authored with Marina, your previous lecturer, and some other people at Perimeter Institute and in Vienna, also in Australia. And the title of this paper is called Relating Wigner's Friend Scenarios to Non-Classical Causal Compatibility Monogamy Relations. Up the archive number, which is at the bottom of the screen. And this paper has been published in the Quantum Journal. So yeah, I mean, the title of this paper sounds very complicated, but essentially it's a paper about non-classical causal models and Wigner's friend. So just to have a recap about causal models in general, and also just to set the stage for our discussion, in this lecture, we will first go through, we will do some review of the previous lecture that was given by Marina about classical causal models and the Bell experiments. Then we will see that just as Marina mentioned in the previous lecture, we already know that the classical causal modeling framework is not sufficient for explaining what we could observe, for example, the Bell correlations in a Bell experiment. And therefore, we know that quantum causal models, or in general, we say non-classical causal models, was developed in the past decade. And the non-classical causal models will be able to explain Bell experiments, but later in the lecture, we will show that these non-classical causal models are facing further challenges posed by the thought experiments related to the so-called Wigner's friend experiment. Okay, so let's first do by the way, if you have any questions, you don't have to raise hand in the Zoom. You can just unmute yourself, interrupt me, and ask the questions. So feel free to interrupt me directly anytime during this lecture. But if you feel shy to just speak up, of course you can write in the Zoom chat. But maybe sometimes I'm not sure if I will notice the messages in the Zoom chat. So if you feel comfortable, the best way to ask questions is just to unmute yourself and interrupt me directly. And don't be shy. Any questions will be a good question, because if there's something that is unclear to you, maybe it's also confusing for other participants. And if you ask questions, maybe you also help other students to learn the topics better. So yeah, feel free to interrupt me. Okay, let's do the recap. First, here just a cartoon illustration of the Bell experiment. So as usual, we use X and y to label Alice setting and Bob setting. And we use the variable a to label Alice measurement outcome and the letter b to label Bob's outcome. Does everyone still remember how the Bell experiment work? Or do you want me to quickly recap the setup of the Bell experiment?
Quickly recap.
Okay, I will, yeah. Sorry, you mean we could do a recap? Yeah?
Yes, please.
Okay, let's just do a quick recap. So in a Bell experiment, what we do is Alice and Bob, we have two observers, or we say two agents in this experiment. They are separated, and usually they are like very far from each other. They are like space-like separated. And Alice and Bob, they at the beginning of the experiment, they will share, for example, an entangled quantum system, an entangled quantum state. So it could be a bipartite qubit state, like two qubits that are entangled. Alice will get one of half of this bipartite entangled quantum system, for example, one of the pair of the qubits. And Bob will get the other qubit in this pair. Then Alice and Bob, they will each measure their share of the bipartite system. So Alice will make a measurement on her qubit, and Bob will make another measurement on his qubit. And Alice and Bob, they have some measurement settings. The measurement settings, for example, Alice's measurement setting is X, and the measurement setting means it's a setting for example, in which basis Alice will measure her qubit, like whether she will measure her qubit in a 0-1 basis. Usually we call it computational basis, like the kind of the z-axis, like the 0-1 basis, or for example, depending on the value of setting X, Alice may measure her qubit in the, say, X basis. Sometimes we also call it the plus minus basis. And similarly for Bob, depending on his measurement setting Y, like say for example, when Y equals 0, Bob will measure his qubit in the basis, or sometimes called the 0-1 basis. And for example, if Y equals, and at the end of the experiment, Alice and Bob, they get together, they collect a bunch of data about the values of A, B, X, Y, and they will they will have a big table with the values of A, B, X, Y for each run of the experiment, and then they will form the statistics, for example, the probabilities of their outcomes A, B, given different settings like X, Y. So that's the basics of a Bell experiment. Now let's talk about classical causal models. Just as in Marina's lecture, here for a causal model, the most important, the central component of a causal model is the causal structure, which is represented by a directed acyclic graph, or a DAG for short. And for the Bell experiment, the natural causal structure for explaining what's going on in the experiment is this one. Because 5 in total. These 4 nodes in triangles, we call them the observed nodes because they are directly associated with the things that node is structure, and called the unobserved node or the latent node, because it directly represents something we observe in the experiment. Instead, it presents the hypothesis that is common cause for Alice and Bob's outcomes. And why do we think there's a common for Alice in the well, obviously in the experiment, we know that Alice and Bob, they share a bipartite and entangled quantum system, for example. So it's natural to assume that there could be a common cause that may be able to explain the correlations between Alice's outcome and Bob's outcome. So since this node is not directly related to things that we observed in the lab, so we call it the unobserved node or the latent node. And in the classical causal modeling framework, an unobserved node or a latent node is always associated with a classical random variable. For example, here we just label this unobserved node using the variable lambda. So this is the classical causal structure for, this is a natural kind of natural causal structure for the Bell experiment. And as Marina introduced in her last lecture, for in general, different causal structure, they can applies certain constraints on the probability distributions that are compatible with it. Or in other words, different causal structures, they can explain different sets of probabilities, because for different causal structure, only those compatible probability distributions can be explained by that causal structure. So for this causal structure that we use to explain Bell experiment, like for this hypothesis, the constraints that it implies on its compatible probabilities we will have multiple constraints, and one of the very important constraints is this factorization condition for the probability for the conditional probability of AB given XY. And so here, as we see that the correlation between Alice and Bob's outcomes, AB, given their settings XY, is factorized into PA given X lambda. Notice that why it's only A given X lambda, because A, the only causes of A is X and lambda. The others are not its cause. So yeah, it's factorized into PA given X lambda and B given Y lambda, because again, the only causes of B is Y and lambda, and then times the probability distribution P lambda, and then we marginalize over lambda to get PABXY. So for any probability distributions that are compatible with this causal structure under the classical causal modeling framework, it must satisfy this factorization condition. And this factorization condition further implies some other constraints. For example, this factorization condition implies the no signaling condition, which says that Alice outcome, given their settings, are independent of Bob's setting. So Alice outcome is here. As we can see, Y is not a cause of Alice outcome. So that's why we have this no signaling condition saying that Alice outcome, even given their settings, is actually Alice outcome given its own setting X is independent of Bob's setting Y. And similarly, we also have Bob's outcome given its own setting Y is independent of Alice setting X. And we call these conditions no signaling because it means that Bob's setting Y cannot signal to Alice outcome A, and Alice setting X cannot signal to Bob's outcome B. So they are called the no signaling conditions. And sometimes they are also called the no superluminal signaling conditions, because if Alice and Bob, they perform their measurement in a space-like separated fashion, then it means that we cannot, they cannot signal to each other with a speed faster than light. So sometimes these conditions are also called the no superluminal. So, right, the factorization condition, it implies the no signaling conditions, and furthermore, it also implies Bell inequalities on P AB given XY. So these are two very important kinds of very important constraints implied this factorization condition. And remember, the factorization condition comes from a causal structure, and the causal structure, your understanding about the causal behind the Bell experiment, causal, meaning that the node is just associated with the classical variable, which we label by lambda here. Good. This causal structure and the classical causal modeling qualities on PAB given XY. Therefore, we know that any classical causal model with this causal structure, which we call the Bell depth, cannot explain violations of Bell inequalities. And this is bad because we have done so much confirming that, in fact, if you do quantum experiment, the Bell inequalities are violated in our laboratory. But the classical causal structure, which we thought is the natural causal explanation for Bell experiment, cannot explain the violations of Bell inequalities. So it cannot explain what we actually observe in the laboratory. However, if you really want to use classical causal models to explain the violations of Bell inequalities, you can do that. All what you need to do is to change your causal structure. In particular, you can, for example, add some arrows in your causal structure. And the arrows, sorry, I forgot to mention the arrows representing the cause-effect relationship. So, for example, here's an arrow pointing from Alice setting X to Bob's outcome B. It means that you think Alice setting X can causally influence Bob's outcome B. Right, so if you use these causal structures instead, then under the framework of classical causal modeling, you will be able to explain why, in fact, we observe the violations of Bell inequalities. However, as Marina mentioned, many people don't like these causal explanations because first, they contradict with certain important causal principles we would like to hold on to. For example, the first one implies that if Alice and Bob perform their measurements in a space-like separated fashion, then this causal relationship between Alice setting and Bob's outcome imply that you can imply that causal influence can be transmitted faster than light. So it implies superluminality, and it contradicts with certain ideas we would like to hold on to according to the theory of relativity. And similarly, the second one, it implies ritual causality because it says, oh, Alice setting X can influence something in the past. For example, the quantum state, the initial quantum state, or the, not really the initial quantum state, the hidden variable maybe governing certain properties of the initial quantum system in the past. Therefore, this one implies that we can causally influence something in the past, and that's why we call it ritual causality, and people may not like it because we know that from our experience, we don't really know how to causally influence, like to change something in the past. And for the third one, it implies the so-called super. One has the ideas that there's some hidden variable lambda in the past that determines causally influence Alice and Bob's settings and outcomes. And it implies that even though, say, for example, in the lab, we thought we are throwing a dice we are all using a random number generator to get to decide in which basis Alice will measure her qubit. Or, for example, Alice thought that she's freely choosing the measurement setting, but in fact, it's determined by something in the past. So it's called superdeterminism. And yeah, different people may have different reasons to not like this kind of causal relations, because continue with the idea that we did. And also equally importantly, all of these explanations, all of this causal structure need fine-tuning to explain the fact that we never observe signaling. Again, the no signaling condition precisely it refers to these two conditions has to have finding to explain signaling. First, recall that use the Bell deck we introduced earlier. The causal structure itself already implies that Alice outcome can never be dependent on Bob's setting Y, even when we condition on Alice's own setting X. Similarly for Bob's changed. So these no signaling conditions are no longer directly implied by the causal structure itself. For example, here, let's look at the first causal structure here. As we already mentioned, this causal structure says that Alice setting X, in fact, can causally influence Bob's outcome B. So in general, we would expect that Bob's outcome B should be statistically dependent on Alice setting X, because they have causal relationships. X is literally a cause of B. However, we never observe such signaling behavior. Therefore, it means that the classical causal models that can explain no signaling must have really specific kind of causal parameters or causal mechanisms telling us about how Bob's outcome precisely depend on Alice setting X, the latent or the unobserved variable lambda, and Y, so that somehow we, because with this very specific causal mechanism, with this very specific functional dependence of B on X lambda on B. And that's what we call fine-tuning. You need to fine-tune the dependence, the functional dependence relation between, say, B and its causes X lambda Y to hide this causal influence from our direct observation. And therefore, from if you think that, why does nature have to do this kind of fine-tuning to hide these kind of things? You might think that these causal explanations are not good enough, because the fact that we need fine-tuning asks for further explanations for why the fine-tuning exists. And it's not in the community, it hasn't been there's no consensus on why this fine-tuning exists, and therefore this is another reason that we don't like these classical causal explanations. Any questions so far? No? Okay, good. Again, if you have any questions, don't be shy, just interrupt me, and yeah, I'm happy to explain or answer questions at any time. Right. Yeah, just to summarize, we have. Hello. Yeah. Yes.
You were coming to summarize. I was about to ask if you could go over it a little bit. This particular area, the problems with classical causal explanation. If you could just go over it a little bit for me. Yeah. Do you get my question? Like, I just want you to explain this part again. Yeah. This from here. Yes, please.
Right. Okay. So there are two kinds of problems with this classical causal explanation. So this slide is about the first kind of problem, which is that these causal explanations, they contradicts with certain important causal principles that we may like to hold on to. For example, the first one, it contradicts with the idea that nothing can travel faster than light. So there shouldn't be causal influence in the case where Alice and Bob, they perform their measurements in a space-like separated fashion. Such kind of causal influence implies that the causal influence must travel faster than light. And so it's in tension with the idea of special relativity. And similarly, the other two causal structure have for example, the second one contradicts with our intuition that we cannot change the things in the past, but the causal structure says that, Alice setting, even if it's in the future of, say, the latent node or the unobserved node lambda, you can causally influence lambda, which is in the past of the setting X. So it's also like, it contradicts with our important intuition about how causality should work, and similarly for the third one. So this is the first kind of problem of these classical causal structures, which is it contradicts with certain important causal intuitions we would like to hold on to about our world, about how causality should work. And then the second kind of problems with these classical causal models is that they all need fine-tuning. And the basic idea of fine-tuning is that in general, for example, if you see the first causal structure, you would expect that in your data, in your experiment, B should be correlated with X, because X is a cause of B. However, in our lab, we know that we never observe such kind of behavior. Therefore, you need very specific functions relating B and its causes X lambda Y, so that somehow, even though X is a cause of B, but because certain very specific causal mechanism, this kind of causal influence is being hidden. So that's we say fine-tuning. Like, you need to fine-tune the parameters between how B, the parameters between X and B, lambda B and YB, so that somehow you never observe the correlation between B and X. And similarly for the other causal structures. And it's in fact proven in these two papers that all classical causal models, if it can explain violations of Bell inequalities, they all need fine-tuning to explain the fact that we never observe signaling, and no signaling behavior refers to these two conditional independence relations. So in other words, we can never observe the violation of these two conditional independence relations. And that's two kinds of problems with classical causal explanation. And here's the summary. Kind of the first kind of problem is it contradicts with certain important intuition we have about how causality should work. And the second type of problems is about the need of fine-tuning, because it's unclear why nature somehow fine-tune these causal parameters to hide certain causal influence relations from us. Is it helpful?
Yes, please. Thank you.
Okay, thanks. If you have further questions, you can ask again.
I have a question. I'm wondering why these dogs are called classical. I was thinking, they are classical models if they obey or if they have locality and maybe realism included in there. But in the first DAG, we see that the X is influencing B. There is no such locality. So how is this a classical polynomial?
Very good question. So here, when I say classical, it doesn't mean that you satisfy locality. It only means that all the unobserved nodes, the hidden nodes or the latent node, is labeled by classical and the variable lambda. That's what it means. Like classical here only means that this kind of unobserved entities is a classical variable. There's nothing strange about this variable. It's a standard random variable. So here classical doesn't mean that you satisfy locality. So kind of here classical is as opposed to quantum instead of classical as opposed to say, I don't know, violation of relativity. Is it clear?
Yes, okay.
Okay, thank you. Any other questions? Okay, I will continue. So, in order to overcome these problems, the framework of non-classical causal models has been developed. And again, here non-classical doesn't mean that we go to relativity or like violations of relativity. It's about how we represent this hidden common cause, this hidden variable. So in the context of addressing the problem with Bell's theorem or the Bell experiment, the main idea of non-classical causal models is to keep the causal structure intact, but we generalize the notion of causality. So specifically in the non-classical causal modeling framework, we no longer require the unobserved node, this common cause, to be associated with our good old classical random variable. And then what happens? We don't have these factorization conditions for our compatible probabilities because we don't have lambda anymore. So you cannot, we cannot even write out these equations because lambda doesn't exist in non-classical causal models. And therefore, you cannot derive Bell inequalities on Alice and Bob's the correlations between Alice and Bob's outcome given their settings X and Y. And therefore, the compatible probability distributions for this causal structure under the non-classical causal modeling framework no longer have to satisfy Bell inequalities, which means that we will be able to explain the violations of Bell inequalities that we observe in our laboratory. More specifically, if we say this common cause is certain quantum entities, then we can explain any quantum any correlations we observe in a Bell experiment using quantum systems. And in fact, if you say that this common cause is certain quantum entity, we can explain the violations of Bell inequalities up to the so-called the quantum bound. Means that we can explain any correlations that can be observed in the Bell experiment with any quantum system. And maybe some of you have heard of the Tsiroson's bound for the CH-SH inequalities, which is one kind of Bell inequalities. But yeah, if you haven't heard of it, it's fine. So here, all you need to know is that if we say the common cause is not necessarily a classical random variable like lambda, we will be able to explain the violations of Bell inequalities, and we will be able to explain any correlations observed in a Bell experiment using quantum systems. So we call this causal modeling framework the quantum causal modeling framework. So far, so good. As far as we are concerned with Bell's experiment, the quantum causal modeling framework is good enough to explain the what we observe in the laboratory. And as maybe Marina has mentioned a little bit, in the past decade, there has been many developments in the causal modeling research community on quantum causal models, and we found a lot of applications of quantum causal modeling framework. For example, it helped us to find other scenarios or other experiments that are not Bell experiments, but we can observe a difference between classical and quantum causal models, which means that it helps us to find certain new scenarios we may see quantum advantages over classical systems. So it has been a very fruitful research area in the past like 5-10 years. But here comes our antagonist of the story. Here comes Wigner's friend, which poses new challenges to our causal modeling technique. In particular, later we will see that the quantum causal modeling framework is not enough to explain the Wigner's friend thought experiment. So to understand Wigner's friend thought experiment and the most recent development on this topic, here is the paper. Here's a review paper if you are interested in it. Okay, I will first introduce the original Wigner's friend thought experiment that Eugene Wigner proposed in 1961. So the original Wigner's friend thought experiment can be thought of as a dramatization of the measurement of the so-called like quantum measurement problem. Maybe you have heard of. Here I will not introduce the measurement problem. I will just introduce this like particular form of the measurement problem, which is the Wigner's friend thought experiment. So in the Wigner's friend thought experiment, we have two observers, Wigner and his friend. Wigner's friend, like his friend, is in a closed laboratory measuring some qubit, and we call the qubit system S. So the qubit is prepared in the plus eigenstate, and the friend is measuring this plus state in the 0-1 measurement in this computational basis. So for the friend, we know that if you measure a plus state in the 0-1 basis, then you have 50% probability to see outcome 0. And we know that if the friend performs the measurement in a minimally disturbing manner, then the quantum state of this qubit will be updated to the 0 state if the outcome 0 is observed. And similarly, for the rest of 50% probability, the friend may observe outcome 1, and the state will be updated to the 1 eigenstate after the outcome 1 is observed. For Wigner, he will have a different perspective because for Wigner, he believes that quantum theory is the most fundamental theory of our universe. So for him, he thinks that his friend is just another quantum system. And in particular, the whole laboratory where the friend is performing the measurement can be viewed just as another quantum system. So for Wigner, and furthermore, as we mentioned earlier, we assume that the laboratory the friend is making the measurement is a closed, it's an isolated system. And we know, according to quantum theory, any closed system, any isolated system evolves according to Schrödinger equation, which is a unitary evolution. Therefore, for Wigner, the measurement done by the friend, which we label by F, and the system S, the spin, can just be viewed as a unitary evolution that from the friend and the spin, their initial state to some states after the measurement. And for example, we can say before the friend makes the measurement, the friend is in the ready to do measurement state. And as we mentioned, the qubit is in the plus state. And then after the measurement, since it's a unitary evolution, so we get into the joint system of the friend and the qubit will be in the superposition of the friend has observed the 0 and the qubit being in the 0 state, and the other scenario where the friend has observed the one, and the spin has been updated, and the qubit has been updated. After the measurement, the friend and the qubit that is measured by the friend will be in such an superposition state, or like they will be entangled. So here we have two perspectives. From the friend's perspectives, after the measurement, for the friend, there's simply just it's simply that the state of the qubit is updated to either the 0 state or 1 state. But from Wigner's perspective, because he viewed the friend also as a quantum system, and the laboratory is a closed system. So for Wigner, the joint system of the friend and the qubit, they evolved unitarily to this superposition or entangled state. So in the textbook or orthodox interpretation of quantum mechanics, looks like these two perspectives are inconsistent. And remember that we got these two perspectives simply by applying the quantum theory we know from our textbook. So it seems strange. And so why in the usual textbook interpretation or orthodox interpretation they are inconsistent? Because in these interpretations, we assume that the quantum state, say psi, for example, the wave function or the quantum state psi, they completely describe the reality of the system of interest. And we have this eigenstate eigenvalue link telling us that a quantum system will have a definite property when it is an eigenstate of some observables. And such a definite property is labeled by the eigenvalue of the observable. So in the first perspective, after the measurement, the qubit is either in the 0 state or 1 state. So it's either have the 0 property or 1 property. Well, in the second perspective, the qubit is entangled with the friend and it's in the superposition instead of only having one of this property. So in the textbook or orthodox interpretations, we see that by simply applying our familiar quantum theory to this Wigner's friend thought experiment, we get two contradictory perspectives. However, if we don't take the textbook interpretation or the usual orthodox interpretation of quantum theory, and in particular, if we don't assume this eigenstate eigenvalue link, then there's not necessarily a contradiction. Because, for example, if we take the view that actually, apart from the quantum state, there could be something else determining the property of the system. So the simple fact that we have two perspectives on quantum state doesn't necessarily mean that in reality, the things are really contradictory. Or, for example, if you think quantum state, they does not necessarily completely describe what's going on in the lab. Instead, it describes what we know or what we think about what's going on. Then there's also no inconsistency, because the first perspective is from the friend, the second perspective is from the Wigner. They have different information about what's going on in the laboratory, in the sense that the friend will see an outcome, while the Wigner is outside of the laboratory. He does not see an outcome. So it's natural to think that it's fine for them to have different perspectives about what's going on in the lab, because they have different information, and the quantum states merely represent their understanding about what's going on in the lab. And so if you think this is the case, there's also just no contradiction. Therefore, the original Wigner's friend thought experiment, actually it does not poses a lot of challenges to the interpretations of quantum mechanics. And why, or like how to say, and maybe we can also understand like why it doesn't pose serious challenges to kind of modern interpretations of quantum mechanics by looking at where these two perspectives come from. So the first perspective comes from the fact that in quantum mechanics we have the collapse postulate about how things should evolve when we do a measurement. And then the second perspective comes from the fact that we have this unitary evolution postulate about how things should evolve when the system is isolated or closed. So the first one is indeterministic and discontinuous evolution, while the second one is deterministic and continuous. So no wonder that we get a contradictory, an apparent contradiction, because we are literally applying two different evolution postulates on the exact same process, which is the process of the friend making the measurement. So it's kind of, this kind of contradiction is a little bit not so surprising, because if you use two different assumptions, or if you use two different postulates for the same evolution, then kind of naturally you will get an apparent contradiction. And that's why in the recent years, people have developed the so-called extended Wigner's friend thought experiment, which built on the original Wigner's friend thought experiment we just saw, and they are a little bit more complicated, and I will introduce one of them later. But before I introduce the details of extended Wigner's friend thought experiment, I just want to emphasize that in the extended Wigner's friend thought experiment, we do not need the collapse postulate. Instead, we will need an assumption called absoluteness of observed events. And we still need the unitary evolution postulate. And we will see that there will be a new kind of contradiction given these two assumptions and some other assumptions. So I will explain this assumption later in more detail. So here I will just quickly say that this assumption is the assumption that when we make a measurement, when we observe some outcomes, these outcomes, they are absolute and single. For example, if we observe spin up, then the fact that the spin is up is an absolute and single thing. It's not like we assume there's no superposition of the outcome that the measurement of the qubit is 0 and 1 at the same time. Because in our everyday experience, we know when we see a measurement outcome being 0, it's really 0. When it's 1, it's really 1. We never see for example, we never see 0 and 1 at the same time. So it's the assumption called absoluteness of observed events. And later I will mention it again. Any questions so far about the original Wigner's friend thought experiment? About the setup, kind of here, the most important thing is we have Wigner and he has a friend, and the friend is making a measurement in a closed laboratory, and we see there's some apparent contradiction between their perspectives. And later, the extended versions of this thought experiment will have more components that I will introduce soon. Okay, I will continue. Let me know if you have any questions. So here I will introduce a specific kind of extension to the original Wigner's friend thought experiment, which is called the local friendness experiment. And it's based on these two papers. So the local friendliness experiment is a combination of the Bell experiment that we saw earlier and the Wigner's friend thought experiment. That's why we call it a kind of extension to the original Wigner's friend thought experiment, because it combines the elements from Bell's experiment as well. So how does it work? In a local friendness thought experiment, so again, we have, just like in a Bell experiment, we have Alice and Bob, who shares a common system at the beginning of the experiment. For Bob, he behaves exactly like how he would behave in a Bell experiment. He has some measurement setting Y, and depending on his setting, he will make certain measurements on the system that he shares with Alice and some outcome B. For Alice, now Alice plays the role of Wigner, and Charlie will first make the measurement on the half of the system that is sent to Alice's side before Alice does anything. So what happens is that Charlie doesn't have a measurement setting. Charlie always makes the measurement in the same basis, in the same way on the system that is just as in the original Wigner's friend thought experiment. Charlie is in a closed laboratory making this measurement, and now we say that instead of Alice just thinking about what's going on in Charlie's lab, now we allow Alice to also do some measurement. Specifically, Alice has a measurement setting X and obtains some outcome A. And we say that Alice can do anything she wants to do on Charlie's laboratory, including Charlie himself and Charlie's share of the bipartite system. So for example, Alice can ask Charlie, what's your outcome? Or Alice can also just take this Charlie's system from Charlie to make some other measurement. So Alice is allowed to do anything on Charlie's laboratory given her setting X, and Alice will make some measurement and get some outcome A. So this is the setup of the so-called local friendliness experiment. And it's a combination of the Bell experiment and the Wigner's friend thought experiment. In particular, in the local friendliness experiment, we require that actually when Alice setting X equals 0, we require Alice to just simply ask Charlie for his outcome and copies Charlie's outcome. So in such an experiment, we require that when X equals 0, A equals C, because Alice simply opens the door to Charlie's laboratory, asks Charlie, what's your outcome, and just copies Charlie's outcome as her own outcome. All right, so previously we said that this causal structure is the natural causal structure for the Bell experiment. Now I will give you maybe half a minute to think about what kind of causal structure you will draw for the local friendliness experiment. And yeah, if you have questions about how this experiment works, you can also ask me. And if you don't have questions, just try to draw the causal structure that you think that can describe this local friendliness experiment. And I saw in the Zoom chat, someone said, asked me to share the paper. So I have already shared the slides to this to today's lecture, and so I will just share it again in case you haven't seen it. And all the papers I have mentioned so far, I have the archive number in my slides, so you can just Google this archive number and then you will see the paper. Okay, so now I will give you my answer, and you can compare to see if this causal structure is the one that you drew yourself. So this is the natural causal structure for the local friendliness experiment. First, as usual, in the causal structure, we must have all the observed variables in it. So here, instead of only having A, B, X, Y, we also have C, because Charlie also makes an outcome and makes a measurement and obtains an outcome C. So we have A, B, C, X, Y. And just as in Bell's experiment, we have common cause for A, C, and B, because this initial bipartite system was sent to Charlie and Bob. So this common cause should connect C and B. But as we said earlier, Alice can do anything on the the laboratory of Charlie, including just simply say, for example, take Charlie's system and make another measurement. So this common cause is among A, B, and C. And he thinks that Charlie's outcome can be a cause of Alice's outcome. And this is because, for example, we said in the local friendliness experiment, it is required that when x equals 0, Alice will simply copies Charlie's outcome. So Charlie's outcome obviously can be a cause of Alice's outcome A. Therefore, this is the natural causal structure for the local friendliness experiment. Do you agree? Or if you have questions? Okay, so nobody says disagree. Now let's look at what kind of probability distributions can be explained under the causal framework. Remember that now we are not in the class framework, so this unobserved common cause, hidden common cause, doesn't be a stated corollary. With Marina, and we proved that. So here I will not go through the proof because it's a bit. Can you hear me? No? Can anyone hear me?
Yes, we can hear you.
Internet problem. Okay, good. Let's continue. So, right. So now we are looking at what kind of compatible probability distributions that can be explained by this causal structure under the quantum causal modeling framework. And so here I will not show you the derivation. If you are interested, you can refer to the paper that I mentioned at the beginning of this lecture. Or yeah, again, okay, I'll just send the document again. So it's in the first slides of this lecture slides that I'm sending in the Zoom. So if Alice and Charlie's outcomes share a very strong correlation, then this I'm very sorry, I don't know what happened. I dropped out again. I hope this time I won't drop out. Let's try again. Okay, let's try again. If it drop out again, if I drop off again, I will try something different. Right. So, for example, if Alice and Charlie share a very strong correlations, then Alice and Bob cannot share a very strong correlation, and that's why they are called monogamy relations. And indeed, in the local friendliness experiment, we know that Alice and Charlie, they do share very strong correlations because we require that when x equals 0, Alice simply copies Charlie's outcome. So when x equals 0, A and C, they have to be perfectly correlated. Therefore, this monogamy relations further implies the certain constraints on AB given Y, which are the so-called local friendliness inequalities from Bell inequalities, and they are in general weaker than Bell inequalities. Weaker here means that there are weaker constraints on the correlations we can observe. So it is harder to violate because they are weaker requirement. Right, so it's something very similar to Bell inequalities, but a little bit different, and it's harder to violate than Bell inequalities in the observations. Okay. Therefore, we know that this causal structure under the quantum causal modeling framework will imply what that means is that any quantum causal model with this causal structure will not be able to explain violations of local friendliness inequalities. And why this is a problem? Oh, sorry, before going to that, here it's kind of side note. So far we have been GPT stands for generalized theories, predict certain things that is beyond quantum theory. So in this lecture, I will not talk much about GPTs. Instead, if you're interested, you can check this archive, this paper. Here's the archive number by Markus Müller for a kind of introduction on generalized probabilistic theory. So in fact, we proved that even if you go beyond quantum theory, go to certain really extreme theory, as long as your causal structure is this one, you will not be able to explain violations of local friendliness inequalities. And this is a potential problem because in these two papers, they have predicted that if we do a quantum experiment of this local friendliness thought experiment, if we use quantum systems, then these local friendliness inequalities can in fact be violated. So how does this quantum realization of the local friendliness experiment work? In this quantum realization, we, just like in the quantum Bell experiment, the bipartite system shared between these parties is a entangled quantum, for example, qubit, two entangled quantum qubits. And furthermore, just like in the original Wigner's friend thought experiment, Charlie is in a closed laboratory, and we assume that Charlie can also be modeled as a quantum system. And then, right, it's a closed laboratory. And then just as in original Wigner's friend thought experiment, if it is a closed lab, then Charlie's measurement process can be, according to quantum theory, it's just simply a unitary. Therefore, what ELAIS could do is that if ELAIS is super powerful, have the extreme technological power to perform like super complicated quantum operations, then when x does not equal 0, ELAIS could in principle apply the inverse of the unitary describing Charlie's measurement process to completely reverse Charlie's measurement, and then ELAIS takes Charlie's share of this bipartite system and make it in a complementary basis from the basis that Charlie has measured. So if we could have this kind of extreme super observer, like with this superpower to perform unitaries on the whole laboratory, then it is proven in these papers that the so-called local friendliness inequalities, or LF inequalities, can be violated in such quantum violations. And therefore, it's a problem that any quantum causal model, or even more general theory, or even more general, like causal models with more general theory, with this causal structure that we think is very natural, cannot explain violations of local friendliness inequalities. So what do we do? Just as before, similar as in the case of Bell experiments, if you want to use quantum causal model for explaining violations of local friendliness inequalities, you can do so by changing the causal structures, like for example, by adding the errors. But also similar as before, all these quantum causal model explanations have undesirable features because, again, these three, each of them will imply some things that we may not like. For example, the first one implies superluminality again, because again, it's saying Alice measurement setting can causally influence Bob's outcome, and the second one may imply ritual causality because Alice measurement setting could be made way after Charlie's measurement. So this causal error means that Alice measurement setting therefore, the first kind of problem with these quantum causal explanations, or even like more general theory explanation with certain important causal intuitions, we would like to hold on to. And furthermore, we prove that any quantum causal model explanations for the violations of local friendliness inequalities, or any GPT causal model explanations, will need fine-tuning to explain the fact that we never observe no signaling. Like no matter it's superluminal signaling, ritual signaling, we never observe them. And in the context of Bell experiment, no signaling just means these first two equations. And here in the local friendliness experiment, no signaling implies these three equations. So here we have the last one saying that Charlie's outcome should be way in the future of Charlie's outcome. So if we believe that we cannot do ritual, we cannot change the things in the past, then, and in fact, we have never observed, we have never managed to change the things in the past. So, so this is the so-called no ritual signaling condition, saying that Charlie's outcome, which is in the past of Alice and Bob settings X, Y, is independent of Alice and Bob setting X and Y. And good. And why we need fine-tuning? Again, as before here, for example, Alice outcome X indeed is a cause of Bob's outcome B, but we never see this correlation or quantum theory, we would never, even though we haven't really done a proper experiment on it, but we cannot believe that we will not see signaling from Alice measurement setting X to Bob's outcome B. And therefore, only with very specific fine-tuned causal parameters that we can hide this causal influence from X to B. So it needs fine-tuning. And in fact, as I mentioned, we proved that any quantum causal explanations or GPT causal explanations will need fine-tuning to explain no signaling. Okay, right, this is the ritual signaling condition. So here, maybe some of you may get a bit worried about the third one. You may say that, maybe we actually cannot experimentally verify this no signaling condition because, as we mentioned, in the quantum realization of the local friendliness experiment, Alice can reverse Charlie's measurement, which implies that Charlie's outcome may be disturbed or erased completely in the experiment. So at the end of the experiment, Charlie's outcome may not be available for us to collect the data and compare with X or Y to see if it's indeed independent of these settings. But in our paper, like in the paper I showed in the first slides of today's lecture, we found some ways to get the operational, like empirical evidence for this no signaling condition. So if you are interested, you can read our paper to check this. Okay, so so far what we invoking a quantum common cause in the Bell deck, but no quantum GPT, or actually in our paper even go further, like we even use some more exotic theory. So none of them with the local friendliness deck, the LF deck, like which is the causal structure that we the natural causal structure for the local friendliness experiment, can explain any violation of local friendliness inequalities. Furthermore, explaining by modifying the LF deck, including direct acyclic graph. So even if you change acyclic to cyclic. So I haven't mentioned this before, but again, the details is in our paper. We show that it will always lead to fine-tuning and the contradictions with crucial causal principles, as we mentioned before, like no superluminal causation, for example. So that's why the local friendliness experiment poses a much stronger challenge to causal modeling framework than Bell's experiment, because we are literally sent back to the conundrum we had earlier when we only had the classical causal modeling framework and the Bell experiment. And that's kind of the most important message of today's lecture, is that even though the quantum causal modeling framework can explain the violations of Bell inequalities, for Bell's experiment, it will not be able to explain the violations of local friendliness inequalities. It will not be able to explain the prediction made by quantum theory for the correlations we will observe in the local friendliness experiment. And if you try to use quantum causal modeling framework to explain it, then you always need fine-tuning, and you will get contradictions with crucial causal principles we would like to hold on. Any questions? Okay, then now we go to the sorry. Yes.
I'm wondering if the Bell the causal structures, if they tell us something about what happens between the measurement settings and then the outcomes, or it just tells us that there's going to be a violation in the case of that kind of experiment, whether it's Bell experiment or the Wigner's friend experiment.
Could you type it? Good. So I will read out the question in the Zoom chat. Is, does causal model outcomes, or does it only go to show violations of Bell experiment or Wigner's friend thought or its extension? Very good question. So causal modeling framework is a very general framework. It's the framework we use trying to explain basically anything we observe in the lab. Like we try to explain why certain things are correlated or anti-correlated. So of course it explains, also tries to explain the link between measurement settings and outcomes. For example, this is maybe not very good. For example, here you see we have a arrow from ELAIS setting X to ELAIS outcome A. So which means ELAIS setting X is a cause of ELAIS setting A. My measurement outcome will depend on my measurement setting. For example, if you have if your qubit is in the 0 eigenstate, then you know that if your measurement setting asks you to measure in the 0 basis, you always get the 0 outcome. Is to measure in the plus minus basis, then you will get 50% of the time the plus outcome, and minus 50% of the time you get the minus outcomes. So you will have a correlation between your setting and the outcome. And this can be explained by the fact that in real life. Any other question?
I was also thinking how a DAG will look like for multipartite settings, like multipartite system. Now it's not just only Alice and Bob, but if we have about 3 settings, though Charlie comes in, but that one is still related to Alice, but they are all independent. And then what it will tell us about
very good question. Yeah, thanks for the question. So now you are imagining a different experiment where we have multipartite system and multipartite parties. So for different experiment, certainly your causal hypothesis, like your explanation for what's going on fundamentally at the causation level, will be different. For example, maybe you let's see, this yellow color is not very obvious. Let me do red. Maybe you have heard of an experiment. So I will just draw it. So A, B, C. So say A, B, C, D. You have, say, a 4-partite experiment where, for example, Alice and Bob can share. So you mentioned that like multi-partite. Oh, sorry, this is not a good drawing. So you can have a 4-partite quantum system in your experiment. Then your causal structure, maybe your explanation will be something like this. So it could be something like that. So you may have a 4-partite, you have a common cause that is related to your 4-partite system that you think can help you explain, say, the correlation between Alice, Bob, Charlie, say, Debbie, their measurement outcomes. So depending on your specific experiment, your causal explanation can be different. And yes, it can model, it can be useful for explaining multi-partite scenarios. Any other question? Go to the last slide of this lecture, which is about, how to say, try to explain why the quantum causal modeling experiment cannot explain the correlations we may observe in a quantum realization of the local friendliness experiment. So this is actually because of a assumption in the causal modeling framework that we haven't been talking much about. So this is assumption that given such a causal structure under the quantum causal modeling framework or GPT causal modeling framework, it is always assumed that there is a joint distribution over all the observed nodes, which are A, B, C, X. The is in fact coming from so-called the absoluteness of observed events assumption we mentioned earlier in this lecture. So in the literature, this assumption says that any observed event, for example, a measurement outcome, is single, definite, and absolute. It is not relative to anything or anyone, and it is not, say, an outcome cannot be simultaneously taking several values. So for example, implication of the assumption is that in the local friendliness, okay, so the implication of this assumption in the local friendliness experiment is that we use a classical random variable for Charlie's outcome, because when Charlie makes the observation, he gets an outcome, and it is an observed event, and it has to be single. It essentially says that Charlie's outcome is just a normal variable. There's nothing funny going on. It's not in his paper for recording outcome. For example, Alice applying the inverse of the unitary Charlie's laboratory to reverse them. You can think of it as a space-time event, that it's a event happened at the time of observation of the outcome. The event itself still exists. It is single, definite, absolute, not relative to anything or anyone. So it can always be represented by a classical random variable, even if its record may be erased. And then similarly, well, just as before, Alice's outcome, Bob's outcome, Alice's setting, Bob's settings, they are all observed events. Like they are all things someone can directly observe in the experiment, and therefore all of them are represented just by a random variable, and over these observed events, A, B, C, X, Y. And this is actually an important assumption derived. So in fact, this is not really really or radical assumption, or like anything, because we always thought that when we observe an outcome, it's just a number labeled by a variable and it takes certain values. We never thought that, okay, when we, for example, do a medical experiment, whether someone recover or not can be a superposition. So it is not this assumption by itself does not contradict with the assumption that any closed system, any closed quantum system evolves unitarily. So this is in contrast to the original Wigner's friend thought experiment, where we used the collapse postulate, which is more obviously in contrast how things change over time. So unit dynamic quantum is somehow how things work. So they briefly same time. And for example, I think Marina mentioned this and Marina mentioned in her lecture about the de Broglie-Bohm, like Bohmian mechanics, or it's called the pilot wave theory. So in the interpretations of quantum mechanics, these two assumptions need to be simultaneously satisfied. So the fact that no quantum causal model with the LF tech can explain well, because there's a contradiction between absoluteness of observed event. Also combined with the fact that we use a specific causal structure to try to we try to explain the violations using the LF deck, the specific causal structure, so that it's all the things combined give rise to the local friendliness inequalities, which is in contradiction with the prediction of the quantum realization of the experiment. And so just to emphasize again, a very important difference between all these extensions of these extended Wigner's friend theorems or arguments as compared to the original Wigner's friend thought experiment is that it's no longer about two different evolution law. We have not used the collapse postulate in deriving the contradiction so far. It's really about the absolute which is about the existence of outcomes, and the unit solution and options the cost we use in deriving the contradiction. And the fact that this assumption like locality to quantum dynamics, for example, in the many world interpretations, there can be not just one out of the relational quantum mechanics. The outcomes, they are relative to the observer that observed it. It doesn't mean anything for other observers. For example, Charlie's outcome doesn't mean anything for Alice. Therefore, in relational quantum mechanics, it is not an absolute outcome. It is a relative outcome. And I know it sounds really, it's a view that's taken by certain physicists. And if you are interested, you can Google, you can search about relational quantum mechanics, cubism, where, okay, so yeah, in these interpretations, the assumption of absoluteness of observed event is being rejected. So they may be able to explain the violations of the local friendliness inequalities in the quantum realization of the experiment. And yeah, again, if you want to learn more about these kind of things, or just learn more about Wigner's friend and its extensions, you can check out this paper. And yeah, and this is the archive number for this paper. So that's it. Please ask any question if you have. And so I will just send all the documents again. So there are 3. So I will have sent 2 documents. The first one is the homework solution for the homework that Marina has given to you. And I will also send the slides of today's lecture in the Zoom chat. And finally, I will send a link. It's a link to a feedback form that we would like to gather your responses. So yes, the link to a Google form where you can write your thoughts about these lectures and help us to improve in the future. And yeah, so that's it for today. Thanks very much, everyone, for attending this course, and it's really my honor to give this lecture. And yeah, if you have questions, please let me know. This is my email address. You can email me. And
Thank you very much.
Thank you. Okay, so I hope I understand that maybe today's content is a little bit complicated. On the bright side is that these are really in the kind of front. It's really kind of cutting edge research happening in the field of quantum foundations and causal modeling. So it's very exciting, and there's still a lot of interesting questions waiting to be explored. And I hope even if you may not fully understand today's lecture content, but I hope it interests these lectures interest you in the field of quantum foundations and causal modeling. And yeah, all the best to your future, to everyone. And yeah, see ya. Thank you.